quantum factoring algorithm. So somebody gives us a composite number n, and we want to find a factor of n and continue with that. So we will find a factor of n with probability arbitrarily close to 1 on a quantum circuit with running roughly in logarithm n cubed. We have logarithm n cubed. Okay, so that's going to be our first aim today. Now, the case 1 will be case if m is 1 is actually exercise 5.4. So we won't be doing that one. So we'll do that later. And we're going to assume n's at least 2. Okay. Now we choose an x randomly in a set somewhere up to n. And we apply Euclid's algorithm. So apply Euclid's algorithm. We're going to apply Euclid. Which runs in bigger logarithm n squared and tells us the maximum divisor of x and n. Okay, so that's just the classical algorithm running in logarithm n squared time. And if this maximum common divisor is 1, then we're done. So if MCD x n not equal to 1, then we have so we have a factor of n, and we can stop. Now, if not, then we saw last time we can apply the order finding algorithm and determine and get R such that it's x VR is equal to 1 modulo n. Now, it is a theorem which I'm not going to prove. So there's a theorem that says, let's write this down for fact, the probability that R is even and x to the R divided by 2 is not equal to -1 modulo n is bigger than 1 minus 1 divided by 2 to the n. Well, unfortunately, I just rubbed it off. Recall that the n is the number of distinct prime factors that n has. Okay, so I assume that this was at least 2, so this is where I use the pattern at least 2, so this is going to be at least 3/4. So there's a good chance that this R is not only even, that x to the R divided by 2 is not -1. Okay? So that means that x r minus 1 factorizes as x to the r divided by 2 plus x to the r to 2 minus 1. This we know is congruent to 0 modulo n. Now, since r is the order, x to the r divided by 2 minus 1 is not 0 n. And with high probability, x to the r plus 2 plus 1 is not 0 modulo n. However, their product is 0 modulo n. Thus, one of them, in fact, must have a non-trivial GCD with n. So we can this one common device. So thus we can apply Euclides. So applying Euclid. We find it. And that's it. Now, of course, if we get unlucky and we get an R which doesn't, we get an X which doesn't satisfy this, if we chose an X for which R is odd, or X to the R come to is equal to -1 mod n, then we simply we will find that out when we calculate the n maximum common divisor here. We just calculate it. We'll see that R is odd, and we can just check that. Then choose different mix. And this will succeed with probability. So it will be 1 minus, so we fail with possible probability 1/4 here. So this will, the probability of success then becomes 1 minus 1/4 to the n if we repeat it n times. So the only thing we have left to mention now in this is that we haven't seen anywhere when we saw the logarithm of n cubed, because actually everything here has been logarithm of n squared. And the other one comes from the fact that in the order finding algorithm, the bit that takes the time, if we recall, we had in the order finding algorithm, we had the unitary that took this to z x to the zy, and this x to the zy should be modulo n. And this x, well, this x to the z is x to the z1, 2 to the, which way round did we do? I think it was 2 to the t minus 1. Where, if you recall, our t was chosen to be logarithm, some kind of like log twice the logarithm of n number of bits or something, a little bit more, to get the accuracy required for the continued fractions algorithm to give us the R. So this will involve doing x to the z1, 2 to the t minus 1, x to the z2. So we need to keep squaring these x to the, so we need x squared, x to the 4, x to the 8th, etc. And each time we do the squaring, that's the logarithm of n steps. And there's logarithm of n, so there's log n of them, each one requiring logarithm n to calculate, could you go from one to the other. And then you need to put them all together to get this, so that's their title with. And when I say logarithm, it's of course bigger of all of this. Yeah? Which is where the logarithm of n or cube comes from. Any questions? Right. So, of course, factoring is an extremely important algorithm to have as soon as we have a, I'm just going to close that window there because that's going to slow things down. As soon as we have a factoring algorithm, certain crypto systems become vulnerable to our attack. Okay, so I went to I watched a seminar the other day, and the guy started by showing a photograph of a quantum computer with 80 qubits. Now, 80 qubits, I have to say, it looked almost identical to an external hard drive. But anyway, it's difficult to see how big it was because it was just a photo, so there was no reference to give you an idea of how large it was. But that's a fully functioning 80 qubit computer. If you think about what we're doing here now, let's think about an algorithm, some crypto system which would require factoring large numbers. So the classic, or probably the very first, was RSA. So let's think about RSA. In RSA, you want to factorize the product of two very big primes. And the reason for that is it works like this. RSA is a protocol whereby I can publish a function, which will be the cipher, that you can use to pass me secret information. Okay, so the idea with RSA is I publish f of x, some function a function f, which you can use to send the x by computing f of x and sending it to me. Now, this f I have chosen cleverly because I've chosen f in such a way that nobody can calculate the inverse. Okay, so f is chosen so that in such a way that f to the minus 1 is basically impossible, is unfeasible to calculate, even knowing f. Okay, so that's so obviously I'm the only person who knows f to the minus 1, so I'm the only person who could then take f of x by f to the minus 1 to recover your secret message x. Now, how would such a function look like? Well, one idea is the following. So in RSA, they say f of x is equal to x to some exponent modulo pq, where p and q are very large primes. So probably it says about 500 digit primes. Now, we can prove that the inverse of this function, is very simple. It's x to the d modulo pq, when e times d is equal to 1 modulo p minus 1 q minus, which note that this is the Euler-Cauchy function of the product of these two primes. And why is this the inverse? Well, we can check that f to the minus 1 of f of x is x to the ed modulo pq, just by checking all the indices. Now, ed is 1 modulo p minus 1 q minus 1. So this is x to the 1 plus 5 pq times some multiple modulo pq, which is equal to x, because this is equal to 1 by what is it? So it's really true that this f to the minus 1 is the inverse. So I claimed here that f is chosen so that f to the minus 1 is infeasible to calculate even when you know f. And you see that's true in this case because to be able to calculate this exponent d, you need to be able to solve this modular equation. And you need to know p minus 1 times q minus 1. And to find out p minus 1, q minus 1 from pq, you need to factorize. So to be able to calculate d, we need p minus 1 times q minus 1, which requires us to factorize. this big narrow EQ. Okay, so that's why RSA is secure, because there is no efficient algorithm to factorize large numbers. Now we've just seen a quantum algorithm which does do that. So let's just take a step back to see if we can now break RSA with that. Here we've got roughly 2 to the 1500. So our logarithm n is going to be about 1,000. Plus I think we had twice the logarithm plus a little bit in our order finding algorithm. So we would need a significantly larger number of qubits than 80. Okay, but I guess the idea being, so we're still okay at the moment with an 80 qubit quantum computer. You're not going to be able to factorize these very, very, very large n's. Okay, so you can breathe again. Another absolute classic of the cryptographic world is the Diffie-Hellman. And the Diffie-Hellman is a very useful protocol which allows Alice and Bob to share some secret information. So this is now another example. So we've had the order finding, we've had factorization, and now we've got another example, which is the discrete logarithm. So in Diffie-Hellman, the idea is the following. Alice and Bob want to share some secret information. They want some secret number together. Okay? And so what they do is Alice and Bob decide to use the integers modulo P for some prime, and agree on a generally set. A multiplicative generally set. Which is open to both parties. Okay, so this G, that means that G squared, and all the powers of G then generate all the primes, all the numbers modulo prime P. So what Alice does, so Alice chooses an A and calculates G to the A and sends G to the A to Bob. Bob chooses a B and calculates G to the B and sends G to the B to Alice. Now Bob has G to the A and B, so Alice and Bob can both calculate G to the AB. Okay, so far so good. So they both managed to calculate this secret number G to the AB. Somebody listening in, traditionally called Eve, can hear, so Eve will, an eavesdropper, Eve, can ascertain G, P, G to the A, and G to the B, but cannot calculate G to the AB. And the reason for this is that the discrete logarithm problem is hard. So the discrete logarithm says, given, well, let's use the same numbers that I'm using here, A to the S mod n and n calculate S. So you've got to determine S. Let's determine S. And you see, that's exactly what Eve has to do to be able to find that G to the AB. She needs to be able to work out one of A or B. Now, this is going to be a little bit more tricky to find an algorithm to solve this. But let's give it a go. So we're going to start off by defining a function. So that in two variables, this f of uv is going to be a to the su plus v modulo n. Now, observe that this f means this, the way that we've set this up here is in such a way that if I now add an s on here to the v, I can take one off the u and I get the same thing. So more generally, if I add on, let's say, L here, then I get L plus S. I'm going to take off LS here to make it the same. Okay, so there's some, the trick is to make this kind of some kind of periodicity. That's right, yeah, because all I've done here by putting the U plus L here is to the next LS and taking off what I substitute here. Now we need a little lemma, so we're going to do so kind of Fourier transform on this f. Let's see. Yeah, I think I've probably got room here. So let's define. Let's do it. Now this is just going to be on the second. Darling, not there or something. So it's going to be 1 over square root of r, j is 0 to e to the 2 pi I w j divided by r f of 0, j. And everything here is going to be constant. There's going to be some base state in the computational basis. Oh, and I missed out on one. And the limit says that this FUV is basically going to be the inverse Fourier transform of this thing. So if we sum this from to R minus 1, then we should have here e to the 2 pi I. We get the S u plus v with the w divided by R, and here, and this of course should all be function sets again. So this should look very, very familiar because it's just doing the inverse for a transform, but it's just now a little bit more confusing because we've got two indeterminates in the F. Okay, but so let's all we want to do to prove this, all we're going to do is stick this into here and change the reverse direction. Okay, so let's just do that. So prove the right hand side here is 1 divided by r, so we get root r and root r. Some, well, let me just switch them straight around because we're just going to switch them in anyway. E to the 2 pi I SU plus V minus JW all divided by R F hat W. Oh, sorry, F hat. Oh, sorry. F of 0. I'm substituting now. F of 0 J. And now you should already be able to see it because it's the usual trick here that if this is not 0 modulo R, then when we sum over the W's, we sum over all the distinct R roots of unity. Well, that's this a number of times, of course. So unless this is 0, this is going to be 0, this sum here of the W. So the only time that that's still 0 is when SU plus V is equal to J modulo R. So there's a unique, so observe, there's a unique J such that SU plus V is equal to J modulo R. Okay, and for that particular J, then we get, so then the right hand side is equal to 1 divided by R. For this particular J, time we get 1 here, we sum it up R times, and here we have this particular J, which was SU plus V. But of course, by definition, this is just the SU plus V, so this is just QV. Which is what we wanted to prove. So now we're going to look at the algorithm. Do I still need that definition? Yeah. Probably. Possibly not. Possibly I just need a limit at the bottom. Let's just leave that one. So the idea of the algorithm is the following. So we choose a t to be log n plus enough cube bits to have enough accuracy to apply the continued functions. Okay, so like before, when we did the order finding algorithm, we had to have, at the end, we applied the continued fractions. And to apply the continued fractions, we needed that alpha minus s divided by r was at most 1 divided by 2r squared. And we get that much accuracy. We can ask for more accuracy by just simply increasing the number of qubits. Okay, so we can have, so we can choose t to be logarithm n plus probably a bit more to get enough accuracy. I'm going to get rid of this one. And the algorithm is the following. So we started with 3 registers. And in the first step, we apply Habermas. So these are all on t qubits. So here we have t, and probably t here. Let me, I guess. So we apply the Habermas case to the first register and to the second register, then these will become U and V. And now we apply our UF. So we have a UF which will take U V 0 to U V F of UV. Okay, so we saw similar unitary operations in the introduction. So this is very important. Yes, so we can take a unitary operation. We can take a classical function f and make a unitary circuit which implements this unitary operation. Okay, so this is a unitary operation. Oh, sorry, not like that. It should be, of course, here, and this should be y plus x. Yes? And this should be y plus. And so now we apply u, and this goes to okay. Now we can use the lemma. So in the lemma, we prove that this and f of uv is really just the sum of the Fourier transforms. So this was then equal to 1 over 2 to the t sum over u, the sum over w, u, v. And how was it? It was e to the 2 pi I su plus v divided by R, missing a W somewhere. Anyway, W. We get that out of in the last register. Okay, so that last one's right there. And I feel I might have missed out a factor of R. So. And now the idea is to rewrite this, again, changing the order of summations. So let's do that. So this is equal to almost 1, 2, 3, the sum over W. And now we want to group these things together, right? So we want to have the U's together and the V's together. So exactly what U's do I have? The U's I have e to the 2 pi I S U divided by R. U and the sum will be 2 pi I V. And all of this with our and now we apply the inverse Fourier transform to both the first and the second register. So now we apply the inverse Fourier transform to both first and second register. And we're going to get something approximation of SU over R here, an approximation for V over R here, and this stays being the Fourier transform of it. Okay. And now we can apply the continued fractions to to determine V over R and then SU over R. No, I got that wrong, of course. No. This, when I applied it here, this was got to the U, so now this becomes FW. Sorry. This becomes SW over R, and this should be W over R, of course, because these V's are gone. Now, by the inverse Fourier transform here, this becomes FW over R, this becomes the W seen here, W over R, and now I can determine if I can fractions algorithm using this estimation for W over R, I can determine W over R and SW over R. And from these two, we can determine S. In fact, yeah, because we can also use the order finding algorithm to find the R. Yes, we already knew R, because R was the order of A. So R was the order of A. So A to the R is equal to 1 show N. That we use the numbering signs. And we can deduce that again using the order. Okay, so it's a little bit more tricky, the discrete logarithm. We need to do like in 2 variables to break it down to get to the S. Right, so about halfway, and that should just about give enough idea of how useful the quantum Fourier transform is when we're writing out quantum algorithms. And now we're going to step into the second part of the algorithms chapter, and we're going to be looking at Grover's algorithm. And this is an algorithm which allows us to speed up a brute force search, so a brute force classical algorithm, by a factor of root. So from n down to root n steps. Okay, so not as impressive as one might hope with a quantum. You kind of would have hoped that you could go from n to logarithm n, let's say, which would then imply that MP problems, for example, could simply go through the whole search space, verifying all your solutions, and since you've got a logarithm speed up, they would suddenly become feasible on a quantum computer. We don't have that, we only have a root speed up, but still it's significantly helpful to be able to solve NP complete problems with a faster algorithm. So we'll talk about that a little bit as we look at Grover's. So the basic idea is we have a function. So suppose f is a function. Make it easy for ourselves by in qubits, and the output's either going to be 0 or 1, for which there exists capital N x's for which f of x is equal to 1. Okay, let's say, let's put capital N to be 2 to the N. Okay, so we've got 2 to the N elements, and M of them, the function is 1, and for the rest of them, the function is 0. So you might suppose that this is some kind of f is a this is so this was some kind of NP problem, then you would be you could calculate. So let's say it was CSAT, you would have a circuit with a polynomial, like an N gate or something, and you want to find out which ones are the X's which satisfy your circuit. So that's an NP complete problem, and you can easily verify if an X is f of X equal to 1. You just simply put it into your circuit and see what the output is. But to determine them all, you have to go through all of the 2 to the N possibilities. So there's no algorithm to be able to determine, no efficient algorithm to determine CSAT. Now, way back when we looked at Deutsch-Jozsa algorithm and defined we defined U of f. Now, U of f given a function f was we took 2 registers x, I, and that went to x. And this x is n qubits. So here we have n qubits, and here we have 1. And this symbol, we call this was addition modulo 2. And we verified some interesting things about UF. We said that UF is unitary, UF fact equals UF emission, UFU is equal to the identity. If you just repeat it, then you get back, you just sum on another f of x, which takes you back to the initial state. And the other interesting thing we noticed about this is if you apply UF to x minus, okay, so that's we call that so we call that minus is 1 over root 2 0 minus. Then here this is going to be what happens to the 0 if f of x is equal to 0. So so let's do the 2 cases. Let's do this as f of x equal to 0. If it's equal to 0, then nothing changes. This is just going to be x minus. And if f of x if f of x is equal to 1, well, when I apply here, this is going to f of 0 is going to when I do it to the 0, this becomes 1. And when I do the x1, this becomes x0. So they flip round. So I get minus x minus. So u of f on x minus is equal to minus 1/3 of x minus. So we want to be able to, we want an algorithm which allows us to determine which of the x's such that f of x is equal to 1. Okay, just give us an x with which f of x is equal to 1. Yeah, so we define the oracle O of x to be this map. Okay, so it's going to take x minus to minus f of x minus. Now the point is here that the function f of x on a classical circuit maybe we can put it together using n gates, but we can only evaluate it. We can only evaluate it one x at a time. But the point is here that if we with this UF and its own x gates, that's what it's these gates, this oracle and this UF, we can feed into that function. So we build the quantum circuit, which is based on the f. It's simply doing this, calculating this f of x, almost, basically. But we can feed it a superposition of states. So we can stick in a superposition, and in some sense, the quantum circuit looks like it's calculating all these f of x's at the same time. Now, that's great news. But of course, as we know and observed before the introduction, we can't look at all of these things. We can only do a measurement and find out one of them. Okay, so we have to make work that to our advantage. Okay, so that's what we need to do. Yeah, so what I should have said, of course, this is just the second thing again. So we define the oracle to be, in fact, this without the minus, right? So because the minus doesn't change, this is now just going to be, okay, so it's kind of UF applied to, and then we just forget about the minus. So in general, so OF, if we have the sum of what's this to so it splits them up into the pluses and minuses, where the f of x is 0 and the f of x is 1. And what we want to do is somehow get into a situation, make a measurement, is going to return one of these values. So what we need to do is get these coefficients here to be large. So we did the measurement, so large ranges. So we're now going to find two vectors. We're going to let alpha be the, if you like, the backways. So remember there are m of these things and n minus n of these things. So if we then let these be the bad guys just by summing up x of x into the other way, then there's n minus n of those. Okay, so we have to divide by square root, so this becomes a unit vector. Okay, so alpha is equal to 1. And the beta is going to be the good guys. And we need to, there's going to be m of those. So we need to divide by the square root again. And our classic state, which is going to be the one we get to by Hadamarding everything. So the sum of all of x. So how do we get that back? Of course, this needs to be unit as well. So we need a state that we can prepare at the beginning, and that's going to be this one, which we can prepare by Hadamard, just setting all the cubics to 0 and then putting the Hadamard in each case. We end up with this one here. Okay, so we should be able to write this in terms of this. So this would be the square root of n minus n divided by n of alpha meter. And this is more commonly and easily written as cosine to sine. So this one's going to be our cosine. So the idea is that we can prepare this state. So this is going to be our initial state we're going to feed into our output. And we want to do something and get close to beta. So that when we do a measurement, we're more likely to get, very, very likely to get one of these x's when we measure the computational basis. Okay, so just to recall, these x's are running over, you could think of them as not really as numbers between 0 and 2 to the n minus 1, but you think of them as the sequences of zeros and ones on the qubits. So as I said, we start with sine, and we want to get close to it. To this beta. Well, what does O of F do to this here? So O of F, if we apply it to sine, that's going to go through all of these alphas in here and not change anything. So it just doesn't change anything, so we just get cosine of theta upon 2 alpha. Whereas when we go through these terms here with the beta, this f of x equal to 1. So when we apply the oracle, it switches the sign to -1. So here we get minus sine with the betas. Okay, so I'm just using this abbreviations. Now, I think this is best looked at geometrically. Let's look at what's happening geometrically. We've got this vector, so we just think of them as vectors, alpha and our beta, and these are perpendicular because they're the sums of different vectors, different elements of the computational basis. So they're all orthogonal. So these two vectors are orthogonal. We can think of them as being 90 degrees. And this psi is a linear combination of these two. So it lies the plane spanned by these two vectors. So somewhere here we've got a phi. And the angle theta divided by 2 is precisely this angle. Because if you think of your Pythagoras here, so this would be the cosine of theta divided by 2 plus the sine of theta divided by 2. Okay, so that's just, this is where we find that angle theta divided by 2. And what does the oracle do here? Well, it doesn't change the coordinate in the alpha axis, but it negates the coordinate on the beta axis. So when we apply our O, we get down here. Okay, so far so good. But now we really covered it. Now we apply so now we apply this map. Let's just see what this does in general. So let's just see, it's easier if you just see what this does in general. So recall that this psi is just the sum over everything. Okay, so the psi is the sum over everything. Okay, so what would happen if, let's just go and name it. No. Okay, so let's apply this to ket phi. This would be twice okay, so that's that. Okay. Where is that in relation to phi and psi? Well, let's think. If this was phi, and here I go a bit longer. What is this is going to be a right angle? Not a very good one. What is this distance here? What is this distance here?
The projection of phi over c, right? Like is what is written there.
Yeah. So it's so simply all unit vectors is from this. So what have we got here? We've got twice this. So here, this is going to now let's draw this again here. Let's get this side. And let's try and work out on this where this vector is. So we've got phi coming up here. Sorry, phi coming down there. let's draw this so it's not in the way. We go twice along here, so now this goes twice along here, and then back along 5. And the resulting is this vector. So what we've basically done is reflect this vector phi in psi. And so we just like flip over the other side. If we go twice up here and then back down here, we've done this reflected it here, you see. So this angle is the same as this. So now if we apply this to OF of psi, we now reflect this whole thing back, and I should have done these things smaller, in this, so this will now become an angle. So now we're going to reflect it in psi, so that's going to be reflected here by an angle phi. So this then goes to this one here. And you see what's happening, we're getting closer to beta.
But doesn't this depend on the angle? Like we may get farther, right?
It depends on the theta, yeah. Yeah. It could be that we go too far over here.
Yeah. So how do we know that?
We'll come to that. Okay?
Okay.
So let's call this thing together the G. Okay, so G. So we do the oracle followed by this Grover. So this is G for Grover. So Grover iteration. So what we prove now is that G of psi, instead of being an angle theta divided by 2, is now 3 theta divided by 2. So we've got cosine 3 theta divided by 2 alpha sine. Now, if I do this again, so now if we're at an angle of 3 theta divided by 2, we reflect down here to do 3 theta divided by 2, and now we reflect all the way back up. We're now reflecting this, so this will now become 3 theta. So I started here, and I ended up here. I should have. Oh no, of course, it's back. So we were here now. So now let's see what happens if we do it again. So this 5, of course, this hasn't changed. Yeah? This is still theta divided by 2 here. But now I am up here when I start, and I reflect in my first reflection reflects in the x-axis, and this angle here is theta 3 theta divided by 2. So I go down to minus 3 theta divided by 2. I now reflect back up in the sine axis, which will give me reflecting back up two thetas, theta divided by 2 minus 3 theta divided by 2. So I go back 2 thetas the other way and end up sort of applying G again. I will go from 3 theta divided by 2 to, what would it be? Theta divided by 2 plus 2 theta. Okay, so this, so I will go down to here and then reflect back up the 2 theta angles when I reflect back up. Now, so that we're at 3 theta divided by 2, we reflect in alpha, that takes us down to minus 3 divided by 2. And now we reflect back in the sine, which is reflecting up 2, which is going 2 thetas past this theta divided by 2. Okay, so I have to put so we get 5 theta divided by 2. And in general, GK then, by the same argument, is 2k plus 1. So now we can work out how many times we want to apply the algorithm, because we need to get to phi, we need it so that we get to theta, which means that we need the angle to be roughly pi divided by 2. So we want to choose k so that 2k plus 1 theta divided by 2 is roughly pi divided by 2. So this is roughly 0 and this is roughly 1. But theta we know, well, we might know, theta, but theta is, we know that the, what was it, which one was the easy one? The sine of theta divided by 2 is square root of m divided by n. So if we know m and n, we can reduce k. I mean, you may know that for example, that your circuit's on has 20 inputs. Capital N is 2 to the 20, and there's a unique solution, so capital N is 1, and then you can calculate your theta divided by 2 from this, and then you calculate your k from this. Now, it may be that you don't know capital N, but we can make a little observation here. So if you don't know N, we observe that in the basis alpha beta, G is a rotation. So G is just rotating things through an angle of theta degrees each time. So that's just your classic rotational matrix. And this has eigenvalues e to the I theta. I mean, this is going to be this eigenvalue e to the I theta because you're going to be if you take away e to the I theta from here, you get minus axis. Should have minus 1 minus 1 0. Yeah, has determined 0. So just thinking about how you find the eigenvalues by subtracting lambda from the diagonal. If you subtract this lambda diagonal and then hopefully you get a singular matrix. Indeed you do. So this has eigenvalues, so we can estimate, so we can use the phase finding algorithm. So phase estimation. Phase finding algorithm from Tuesday's class to determine theta. So that's great. So let's have a look at an example. I guess we should be somehow pointing out that that the number of things is going to be about root n in general. Just trying to see how we see that. But the sign of theta is k is going to give us the number there. So the sign is roughly for small things, roughly the same thing. So the theta is going to be roughly 1 divided by n. Yeah, I'm just working this out. Yeah, I forgot to do this before. So we had, I think this is kind of a heuristically kind of argument. So we had 2k plus 1 theta should be divided by 2 should be something along the lines of pi divided by 2. So, and we had that sine of theta divided by 2 was something like square root of n divided by n. So, assuming this is small, sorry, divided by n. Assuming this is small, then this sine is approximately going to be square root of n divided by n. So, it's not. Sorry, the sine is roughly going to be equal to roughly divided by 2. So we'll have 2k plus 1 here, square root of n divided by n, pi divided by 2. So k is some. So n is bigger than 1. case big overruling. Okay, so it's just a brute force we can go through. Instead of having to go through all 2 to the n, it would be 2 to the n divided by 2. So iterations rather than having to go through all of them. Okay, so it's a square root speed up and not logarithm, and that's the real shame, because it doesn't suddenly, if it would have been logarithm, you see, it just suddenly turns all NP complete things into polynomial time solutions, because you simply go through all the possible solutions, all your 2 to the n things, and run it through your circuit with the logarithm speed up, and you will be able to solve NP complete problems in polynomial time on quantum computer. We will see next time that these brute force, this is the limit of a brute force algorithm on a quantum circuit. So it's tempting to think, oh yeah, maybe Grover just didn't get it quite right, and actually there is one which is logarithm speed up, but we'll see that that's not the case. Now that it could be because this is just brute force and we're not using something more subtle, and that probably would require something to know something more about the problem. If you think about the factoring and the order problem, there's some extra periodicity in the problem which we are making use of. So it would somehow require problems like circuit satisfiability to have some kind of hidden extra property which we haven't quite seen yet, but that's not impossible. Okay, so let's just use the last 20 minutes to have a look at a nice example, which you can see that this really works. So even though it's small, it's still I think it demonstrates that. So this is going to be n is 4. So we've got 2 input bits. So let's see what the oracle would look like. So the oracle for f. So let's say f is a function on 2 qubits. So f of x is equal to 0 for all x not equal to, let's say, x naught, and f of x naught is equal to 1. So the oracle for f is 1 of. So how would you qubit this up? Well, let's say it's let's say that x naught is equal to 0, then this would be your oracle. And what will come out of here? So this is going to be a 1 coming out of here, so you put a 0 in here, and a 1 is comes out as 1 if and only if x, the input here is x, if and only if x is equal to 0. Okay, so remember this is the opposite, this is controlled on the 0 here. And then you would do the other one similarly. So if you were controlled on a 1, you would want to have 1, 0. So this would be a control, this would be control on the 0. I wanted to C naught there, didn't I? C naught down here. And this is going to be the case if x naught is 0 to 1. Okay, so this is going to be your oracle in case x naught is equal to 1. we put x here, and out comes one if and only f is x naught is 1, x is 1, and then the other two cases will be the other way around. And then properly. So you need both of them set, and then it switches it to 1. Okay, so that will be your oracles for the different f's. And this is the circuit that we have just described in this case. So remember we had the minus in the last register. So we would have Hadamard's to begin with, because we're starting with 0 and 0 here, and we need to put them in all into superposition. And down here, we start with a 1, because when we're going to Hadamard it here, or we can just start with 0 and put an x first, Hadamard it here to get into a minus. And we feed these things into our oracle. And now I'm going to draw this and then explain to you why this works, why this is implementing Bremer's algorithm. These h's we will ignore for the moment. We'll put x's here, and then we feed the h, c naught there, h, and then back the other way with 2 x's. And h. And this stays the same throughout, and if you like, we can Hadamard it back to 1 at the end. Now, what I want to convince you is that this first, this bit of the circuit will implement the following unitary operation. Well, actually, let's just, yeah, okay, no, okay. And that operation is the following. It is twice 0, 0, 0, 0 minus the identity. And we can just check this. So this is the box, And so we will be back into the familiar territory of Lemma quadrant. So 0 is 0, x, that's going to go to then 1, 1. Hadamard on the second is going to go to 1 plus. Now, C naught, so we're going to switch it, but switching it doesn't affect the plus. It just takes the 0 to the 1, 1 to the 0. So doing the C naught and the plus is just, well, in fact, plus. Another way of looking at that is plus is an eigenvector of eigenvalue 1 of x. So this just goes, this stays the same. It then gets hit by this Hadamard, so it goes back to 1, 0. I'm not a bit worried, because this should have changed at some point. Ah! When I hit the Hadamard here, this goes to a minus. Are you still there? Are you paying attention? So when I hit the Hadamard here, this is the x1, x2. This is Hadamard in a second. So then when I press the C naught, so this is the C naught, then yes, it changes. So minus, as we saw before, minus is a eigenvector of eigenvalue minus 1 for the x. So this is now minus that. And now I hit the h and the x. H2 goes to 1, 1. still the minus, and then do the x1, x2 again, goes back to minus. Okay, so that's not exactly what I claimed it would do. If I take 0, 0 in here, I get twice 0, 0, minus 0, 0. It's the other way around. And whereas the other ones, of course, when I do 0, 1 here, it's not going to, it just gets annihilated. And here we get 0, 1, so it shouldn't change at all. So let's, how much time have I got? Not that much. If I do x here, then I do the Hadamard 1 plus. Now I do the C naught, the plus is an eigenvector of x of eigenvalue 1. Then I do the h, so that goes then back to 1, 0. Then I do the x of x, gets back to 1. And the same thing happens here. I mean, the only thing you have to slightly worry about is when you get the minus here. But when you get the minus here, you're going to have a 0 here, you'll see. So that's why it works. So that's coming up now, 0 minus. And because it's controlled not, you don't do anything because you've got a 0 in the first bit. So now it goes back to 0, 1, and 0, 2 x's, and a 1, 1. So 0, 0, 0 minus, 0 plus, 0 plus, back to 0, 1, 0, 0. I always get the answer. Okay, so this is indeed the box. But of course, it's not that box that we've got Hadamard excited. Why have we got Hadamard excited? Because we're going to change these 0, 0s into plus pluses. And what's the plus pluses is exactly sum. You see? So I'm now going to get rid of this calculation here, and you can, that's a good exercise for you to check. So now I'm going to take this and I'm going to Hadamard both bits. So h1, h2 of I minus 2, 0, 0, 0, 0, followed by h1, h2. So I'm saying this is h1, this is h2. Well, that's going to be, so, well, these are commutative, obviously. So h2, h1s. So here the h2s are Hermitian and self-inverse. So they go here, so this is just identity. And here I get minus twice, plus, 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 plus. Well, what is a plus, 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 plus? Well, it's just nothing more than, sorry, the sign was again the sum of all squares. Yeah, so. And maybe we want some normalization factor there. So if I've got 4 states, it would be a half in this case. Now, how many times should we be applying Grover's? So the sine of theta divided by 2 is the square root of n, capital N, which is 1 in this case, and 4, which is the big capital N. So that's 1/2. So that implies that this is 0.9 by 6. So theta is divided by 3. So we have 2k plus 1 theta divided by 2 is pi divided by 2, which implies now that implies that K should be 1. So in the last 5 minutes, let's just see what happens, yeah? So let's just put the thing into the circuit and see what happens. So we start with our superposed state at a minus, and we stick it in. So what was this? This is half 0, 0 plus plus 0, 1 plus minus. And we put it through our oracle, which flips the sign of the correct solution. So let's say that the correct solution was x naught is 2. Yeah? So this is the 1, 0. Yeah? So the 1, 0 is the correct solution. So when we stick this through the oracle, it's going to flip the sign of this. And now we do, and now I'm going to apply I minus twice this thing. Okay, so I can write this is effectively psi minus 1, 0. Okay, because sum of the half of all of them, and then we've got to sum, we've got to take this away to go from plus that half to minus the half. So now when I apply this, I get psi minus 2 psi minus 1, 0. Now one is, minus twice 5, 1, 0. And this minus is a minus, so it should be a plus. And what have I got here? This is minus psi minus 1, 0. And this is a half, so I get a plus psi here. And I brought the answer for this 1, 0 up to play the face. I think I've got to sign, this is somehow the minus the Grove iteration, but it doesn't make any difference. All of these at the end, we end up with an extra minus sign here. But when you do the measurement, you will measure 1, 0 with probability 1. Isn't that brilliant? So you may like amuse yourself and try and work out 3 qubits. Might take a long train journey, but yeah. So that's Grover's algorithm. As I say, so we'll leave it there for today. Now I'm going to stop the